Hello friends, welcome to engineering tutorial. Now in my previous video we discussed about the concept of rectification and the half wave rectifier circuit. So we discussed about the circuit diagram, the circuit behavior during the positive and negative half cycle of the AC waveform, the efficiency of the half wave rectifier and the input and output waveforms and frequencies. So in today's video we will discuss about full wave rectification concept, and we will discuss one of the subcategories of full wave rectifier, which is the center tap full wave rectifier. So let's get started. Again, first the basic definition, the basic concept. So what is full wave rectification? Now if you remember, in half wave rectifier the current conduction took place only during one half cycle of the AC, that is the positive half cycle. Okay, so if you see, AC has two half cycles. This is the positive half cycle, this is the negative half cycle. In half wave rectification, current conduction took place only during the positive half cycle and no current conduction took place during the negative half cycle. But in full wave rectification, current flows through the circuit through the load resistance during both the half cycles. So I suggest that you please check out the half wave rectification video first before you go into this full wave rectification, so you understand this in a better way. So in full wave rectification, the current flows through the circuit, that is the load resistance across which the output voltage is taken, in the same direction during both half cycles, that is the positive and negative half cycles. As you can see here, both during the positive and negative half cycles there is output that we get through the load resistance. This is again pulsating DC output, we will get to it. So full wave rectification has current conduction taking place during both the half cycles, that is the positive and negative half cycles of the input AC. So this is generally done by using two diodes. In half wave rectifiers we used only one diode, but here in full wave rectification two diodes are used which work alternatingly, turning on and off to produce current conduction during both the half cycles. So we will discuss how this happens. So types of full wave rectifier, as I said earlier, the full wave rectifier generally comes in two configurations. First one is the center tap full wave rectifier, which we will be discussing in this video, and the bridge type full wave rectifier. There are certain disadvantages of center tap full wave rectifier, why the bridge rectifier is used for that reason, and the bridge type rectifier will be discussing in a separate video after this. So first, the center tap full wave rectifier. So first let us discuss the components that are used. Almost all the components are the same as that of the half wave rectifier. The only there are two differences. Okay, first one is there are two PN junction diodes instead of one. In half wave rectifiers we use one PN junction diode, here we have two PN junction diode. Then we have the usual step down transformer. The second difference is that a center tapped secondary winding is used. In half wave rectification there was nothing like a center tapped winding, secondary winding, but here we have a center tapped secondary winding. Then we have the load resistance, then we have the AC supply, which is the input 230 volt and 50 hertz supply that we get. So all these things are the same as the half wave rectifier, only two differences, one extra PN junction diode and a center tap secondary winding. So this is the circuit diagram of a full wave rectifier, that is the center tap full wave rectifier. So here we have is the AC supply, which is connected across the primary winding of the step down transformer. The AC supply is 230 volt 50 hertz. the step down transformer converts this 230 volt AC into a lower voltage level, generally 12 volt, but there can be other values as well. For that, different configuration of step down transformers are used, but generally 12 volt, 230 to 12 volt step down transformer is used. This here is the center tapped connection, which is exactly in the middle of this secondary winding. Okay, exactly in the middle of the secondary winding. There is a center tap point which is connected to one end of the load resistance, while the other end of the load resistance is connected to the two PN junction diodes, the N-type ends, okay, the N-type ends of the two PN junction diodes. The two ends of the secondary winding are connected to the P-type ends of the PN junction diodes D1 and D2. The output voltage is taken across this load resistance. Okay, so we get a DC output across this load resistance. Now, how do we know that it is DC? Because the current flows through the load resistance only in one direction. We will see how that happens. Okay, so this is the basic circuit diagram of a center tapped full wave rectifier. Now, let us understand the circuit behavior. So, again the same process during positive half cycle and negative half cycle, we will study the behavior of the circuit. Okay. During the positive half cycle, the top end, it becomes positive of both the windings, mean A becomes positive and B becomes negative. In this case, the P-type end of D1 is connected to the positive terminal because A is positive, while the P-type end of D2 is connected to the negative terminal. So, when this happens, when the P-type end is at a higher potential, the diode behaves as a forward bias diode and behaves as a short circuit, and when the P-type end is at a lower potential, it behaves as a reverse bias diode and is open circuited. So, in the positive half cycle, when A is positive and B is negative, diode D1 is forward biased and behaves as a short circuit, while the diode D2 is reverse biased and behaves as an open circuit. Diode D1 is on, diode D2 is off. So, a current flows through the circuit in this loop, okay, AO, okay, current flows through the circuit in this loop, okay, in this closed path. So, the current flows through the load resistance in this direction, okay, this direction. This is the direction which is represented by the arrowheads, the current I, and the output is taken across this load resistance. Next, during the negative half cycle. Now, during the negative half cycle, the polarities are interchanged. B becomes positive, A becomes negative. Now, in this case, the P-type end of D1 is connected to A, which is negative, okay, A which is negative, the P-type end is connected to that end, and B which is positive, the P-type end of D2 is connected to B. So, as a result of that, the diode D2 is forward biased because it is connected to the point B, which is positive, because the polarities are interchanged during the negative half cycle. A is negative, B is positive. P-type end of D2 is connected to positive end. P-type end of D1 is connected to A, which is negative. So, for that reason, D1 is reverse biased, it is off, it is open circuited, while D2 is forward biased, it is on, it is short circuited. So, as a result of that, no current flows through in this loop, but a current flows in this closed loop. So, as you can see, the direction of the current in both the cases during the positive and negative half cycles are the same. Okay, the current flows from right to left, okay, from right to left towards the center tap winding. Here also it is flowing from right to left towards the center tap winding. Okay, so in both the cases, the direction of flow of current stays the same. This is a very important point. Okay, in both the cases, here the current flows in this direction from right to left towards the center tap winding. Here also the current flows from right to left towards the center tap winding O, towards the point O. Here also it flows towards point O. Here also it flows towards point O. So we get a pulsating DC output because the current direction stays the same during both the positive and negative half cycles. Even though one of the diodes stays off, but current conduction is goes on uninterrupted. It does not get affected because of the use of two diodes. But in half wave rectification, the disadvantage was that one diode was used, so one half cycle of the input AC was wasted, was not utilized. But here, because of the use of two diodes, both the half cycles, positive and negative half cycles, are utilized and we get pulsating DC output. So as you can see here, we have the input AC waveform 230 volt 50 hertz. This is the positive half cycle, this is the negative half cycle, and during both the half cycles we have pulsating DC waveforms. Now the output and input frequencies. Okay, this waveform is one complete cycle of the input AC 230 volt and 50 hertz from here to here. This is one complete waveform, one complete cycle. So when one cycle of the input AC is completed, we get two complete cycles of the pulsating DC output. One complete cycle of pulsating DC is from here to here, because DC does not have a negative cycle, because it is DC. Okay, it has only one, the current flows only in one direction. So that's why from here to 180 degree, it constitutes one cycle of pulsating DC. From here another cycle starts. So during one complete cycle of the input AC, we get two complete cycles of the pulsating DC output. It means that the output frequency is twice that of the input frequency. For during one complete cycle, or for one complete cycle of the input AC, we get two complete cycles of the pulsating output DC. So because of that, the output frequency is twice that of the input frequency. Now this is the pulsating DC output. Again, a smoothing capacitor, electrolytic type with a high discharging time constant, is used to convert it into smooth DC or almost flat DC. This is pulsating DC. So a separate video I will post about that, how this process takes place. Next we have is the efficiency of the full wave rectifier. We discussed about the efficiency of half wave rectifier. There is a complicated lengthy expression or derivation part is there, which is very long to be accommodated in this video, so I will be posting it in a separate video. So for now, just note down this expression. Efficiency of any device is defined as output by input. So in half wave rectifier, it is DC output that we get for AC input, application of AC input. So the efficiency is the ratio between DC output power and the AC input power. So it comes in this form, 0.812 by 1 plus RF by RL. Here the small r subscript small f is the forward resistance of the two diodes. So I have discussed about the forward resistance concept in the PN junction diodes introduction and the other concepts. So please check out that video. So forward resistance is the ratio between the forward voltage and the forward current, and RL is the load resistance which we have used. So this ratio RF by RL is very less and is negligible as compared to 1, so it is neglected, and we get efficiency as 81.2%. Now you please take note that the efficiency of the full wave rectifier is exactly twice that of the half wave rectifier. For half wave rectifier, the efficiency was 40.6%. So for full wave rectifier, it is exactly double, twice that of half wave rectifier. okay, 81.2%. So here we have discussed about the concept of full wave rectification, the types of full wave rectifier. So in full wave rectification, current conduction takes place during both the half cycles of the input AC, and no half cycle is wasted, means no energy is wasted. And the full wave rectifier is of two types: center tap full wave rectifier and bridge type full wave rectifier. Now you will ask a question that why do we need this bridge type full wave rectifier? What is the disadvantage of center tap full wave rectifier? Now one disadvantage or demerit, the main demerit which is which this center tap full wave rectifier has, is that the exact location of the center tap point, the middle point of the secondary winding, is very difficult to locate. Okay, so this makes this process, this design of this circuit very difficult. So for that reason, the bridge type full wave rectifier circuit was designed as an improved version of full wave rectifier to correct the demerits of the center tap full wave rectifier. Here in this bridge type full wave rectifier, there is no need for locating a center tap secondary point. This connection is not used, so it is very difficult to locate the exact middle point of the center tap point in the secondary winding. So for that reason, the bridge type full wave rectifier is used. So we'll be discussing that in a separate video. So we discussed about the circuit diagram, the circuit and the circuit behavior during positive and negative half cycles, and we discussed about the input and output waveforms and the frequencies, the comparison between output and input frequencies, and the efficiency of the full wave rectifier. Now, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electronics, electrical, instrumentation and communication engineering. Have a great day. Thank you very much.